V, V. Right. So the first step, theta C. Did you get theta C? You see that theta C is 1 over mu, and mu is mu gross minus B. Right? And then we could get theta. It's from XV. You have S0, S, Y, B, X, theta C. Therefore, you can solve theta. Right? Theta is 0.13 day. Of course, if you have theta, you can solve V, volume. All right, volume. Volume of the aeration tank. And what next? Recycle flow, right? Recycle flow. You can determine recycle ratio. Recycle ratio. But here, XR is missing, so you have to assume XR. Recycle ratio is about 4.4. And then we need to design the second clarifier, right? It's empirical, therefore we assume 1 over flow rate. And here we still use 25 and get a surface area of the clarifier, 1514 square meter. And finally, we determine the waste flow, QW, right? QW. QW is from the definition of theta C. This is not the Q, okay? This is theta C. Theta C. That's a typo. Theta C. All right. So how many of you have got this? It's very easy. First step. Yes. So you get 405 points. How about this step, theta? Anyone got this? Theta value? No. If you cannot solve theta, you cannot solve other steps. Right? You have to use all these equations very efficiently. Please. Right. So XR is something we could assume. XR is typically between 10,000 and 12,000. That is a typical value for secondary clarifier. The performance. It's kind of empirical. Any other questions? Any other questions? Nope. Okay, so let's do one more. Right, one more. Active sludge. So we know Q, we know S0, we know the V, we know the XV, yield, Y, decay, B. Solids in return sludge, XR or XW. Solids in effluent, XE, BOD in effluent, S. This one is very easy. Determine the sludge H, theta C, right, QW. This is simple use of the equations. 10 minutes. One is easy, right? No? Do you want more time or just look at solutions? Right. For the first, I notice many of you have reached the first step. Right. From XB, you can solve theta. Oh, sorry, you can solve theta C. We can calculate theta. Right? Then from theta C, you get a QW. Is it? By using all the expressions again and again and again. Therefore, you should be familiar with them. Okay. Any question? No? No? Okay. So let's look at one more. So final. Right. Determine theta C. Or just focus on the first. Theta C. Focus on problem B. Just ignore, sorry, problem A. Just ignore B and C. How to solve A? Okay, within a few minutes. All right. So the first, right? XV times V minus, divided by QW XR. Should be XR, not XE. Right? So that's definition of theta C. Definition of theta C, 6.36. Day. 6.36. Okay, ignore problem B and C. Let's see how many slides I have. Okay. Let us take a break. Take a short break. All right, so let's continue. During the break, many asked about the question why we ignore XE here, right? For the last problem, in class problem. So typically the effluent concentration of effluent cells concentration is low. XE is low, so we can safely assume XE is 0. Right? This is one example. When you compare this term with this term, right? So this term is quite small. So generally that term is small. It will not affect this number a lot. That is acceptable from an engineering perspective. Okay, engineering perspective. Right. So therefore, you see, in many cases we assume XE is 0 and we omit this term, right? We only have XV times V divided by QW times XR for theta C. Okay. All right. So all this process modeling about active sludge, aeration tank, secondary clarifier, right? And for active sludge, we could have certain modifications, right? The first one is aeration. Aeration, yeah, different bubble aeration, different flow rate, and it could have mechanical mixing, right? Mechanical method to supply oxygen into the liquid. And we have different turbines, surface aeration, turbine aeration, and design DO is 2 milligram per liter. And step aeration, right? Step aeration, we mentioned this a little bit. It's modification of plug flow, PFR, right? But introducing waste at different locations. At different locations. There's no mixing in PFR. Okay, no mixing. So at the beginning, if it is conventional PFR, the waste introduced at the front end, right? So here is the highest concentration. Another tank, the concentration of substrate decreases because of degradation, right? And that's a problem in some cases because the requirement for everything is high at the front because you have high concentration, right? And by introducing the waste along the tank, you can average out the demand. This is step aeration. Step aeration allows greater flexibility of operation. And then we have another extended aeration, a modification used for small, low maintenance plants. The system could be plug flow or CSTR. We use long theta C but low loading of BOD. Theta C is 20 to 40 days. It's longer than typical active sludge. Typical active sludge a few days, but here it's 20 to 40 days. Right? Theta 18 to 36 hours. Recycle ratio 0.75 to 1.5. MLVSS 3,000 to 6,000. And the process is generally used without primary settling and on small packaged plants, a small scale. And often no sludge is wasted, right? Because you have high theta C. What is theta C again? Theta C is 1 over mu, right? If you have very large theta C, you have very small mu. What is mu? What is mu? What is the definition? Net specific growth rate, right? So that is growth of cells. You have very long theta C, you have slow growth, right? Slow growth. So cells grow slowly in the extended aeration tank. Therefore, we cannot waste because the concentration is already very low, right? You do not have space to waste. And this is the schematic. So there's no waste stream. No waste stream. Contact stabilization. Basically, we separate the aeration tank into 2 tanks. One is aeration, the other is contact. Because we think that the degradation process has 2 steps. The first step is to contact or adsorption of substrates onto the suspended solids, right? The second step is degradation. So we can separate these 2. And for the contact tank, theta is half an hour to 1.5 hour. In aeration tank, 3 to 6 hours. 2 phases. The ideal here is to separate the absorption and assimilation stages of substrate utilization. The advantage is volume requiring aeration is 1/2. Right? So imagine you originally have a very large tank. After separation, you have a smaller aeration tank, half of size. It's more efficient, but you can imagine for that smaller tank, you need to supply more oxygen, right? More oxygen. Therefore, you need bubble oxygen gas instead of air. Oxidation ditch here, recirculation. Okay, recirculation. We'll just take a look. Maybe I'm not going to show the full video. I'll leave to you to watch. Right, so here, circulation. Right, SBR, sequential batch reactor. We have it's not continuous flow, right? By its name, it's batch. So 5 steps: fill, react, settle, draw, and idle. Right, all the steps happen in the same tank at different time. Can you imagine SBR used for small scale because it's not continuous flow. The small scale treatment. I'll skip this kinetics in SBR. So we do have SBR operated in Hong Kong. Okay. That is used for treatment of non-field nitrate. Okay, non-field nitrate. We have a few large non-fields, right, in new territory in Hong Kong, and the nitrate should be treated before being discharged into public sewer. And this is the schematic of a process flow chart. We have rows, nitrate, and we remove ammonia first, and then SBR, and then to the public sewer. Right. So these are the tanks, SBR tanks, pretty large. Okay, pretty large. These are ammonia stripping tower. Okay, and also in some other isolated areas like correction of facilities, etc. Okay, SBR. Look at the treatment capacity, a few hundred cubic meters per day. It's a very small flow rate. Oh, not flow rate. There's no flow, right? It's kind of capacity. Right. So that is what we have covered. Different variations of active sludge. Right. Continuous flow. You could have CSTR. You could have plug flow, PFR. You could have step aeration. Right. You have oxidation ditch. You have extended aeration. And for batch, you have SBR. Okay. So comparing, let's compare PFR with CSTR. This PFR, this CSTR. PFR typically rectangular, CSTR circular, right? Circular. They have certain differences in theta C and MLVSS, right? MLVSS. CSTR is better for toxic wastes. Why? What is CSTR? Constant stirring, right? This complete mix. Because if you have a shock or sharp increase in toxic concentration, CSTR can quickly what? Average out the concentration, right? Because it's complete mix. But for PFR, you always have the highest concentration at the front. Okay. Some comparison. Look at SRT, right? So typical few days for active sludge process. HRT a few hours. Right. So design notes. This is a summary of what we have done for all these practice problems, right? So typically we are given Q and S0 wastewater flow, and we also know the waste type, like the yield, like the K, Ks, and B. And there are 5 design variables: theta C, XV, XR, V, or theta, right? So V is connected to theta. Theta is V divided Q, right? And R, recycle ratio. I'm not counting U, safety factor, S, QW, QR. All these are interrelated to some of the above. So in general, you may choose 3 out of 5, and the other 2 will be defined. Okay, so 3 out of the 5, and you determine the other 2. Typical design steps: assume theta C or U, or F to M ratio or safety factor. Right? We still remember the two examples. The first example, we calculated the theta C minimum. We applied a safety factor. We obtained the theta C design. Right? For the second exercise problem, we calculated mu first. Then we get theta C equals Y equals 1 over mu. Right? So we determine theta C. This determines mu and epsilon S. And then assume XV or V. Right? You either assume XV or you assume tank size. Right? In our exercise problems, we assume XV, 3,000, 4,000 milligram per liter. Then we determine the tank size. Right? Tank size V. But XV or V are connected through this expression. Right? Through expression. So in our practice problems, we have picked a value for XV, and we determine theta or determine V, the volume of the tank. Right? And then assume XR or R. So typically we assume XR between 10,000 to 12,000 milligram per liter, and there you can determine recycle ratio. Right? There is no single right answer to design problems. Right? A range of theta C or U values are acceptable. There is also a range of reasonable XR and XV. For example, XV could be between 3,000 and 5,000. Right? So you can pick 3,000, 2,000. XR 10,000 to 12,000. You can pick 10,000. You could pick 11,000, 12,000. Right? Some design variables are interdependent. Okay. Consider these 2 slides. Connect these 2 slides with the practice problems. So step by step, what we have done. Right? What we have done. All right. Okay. Any question before I move to the next topic? No. So far we have been talking about active sludge, right? The most common version of suspended gross treatment scheme. Microorganisms are suspended in water. Now we switch to attached gross treatment scheme. Microorganisms are attached, right? Attached. Please read corresponding book chapters. Okay, right. And we see that microorganisms are attached to certain surface. Therefore, we have methane in attached gross treatment systems. This is a trickling filter. Okay. So remember, trickling filter is not a filter. It's not like sand filtration. It's not like membrane filtration. Although we call it a trickling filter, it's not a filter. Okay. This is a trickling filter. You see a lot of all this media. Okay, these are made of plastic or some other synthetic materials, and they could have different configurations, creating different water flow patterns. Okay, and this media provide the surfaces for microorganisms to grow. Okay, so this is very different from the suspended ghost scheme. Okay, scheme. Look at this. So look at the space in between the media. It's very large, so you cannot perform the filtration function. Therefore, we cannot say trickling filter is a filter. Make sense? Okay, you can fill out nothing. Okay, so here still we utilize microbial function to degrade organics. Okay, degrade organics. We have different ways to distribute water to the media. Okay, you can see here we have some spray nozzles, right? Wastewater, and this trickling filter is made of rocks, and some media are rocks, some are plastics. Okay, different materials. It could be very large trickling filter. Okay, huge. This is the distribution arm. Okay, this is media. Okay, right, the media, different flows, the cross, vertical, incline, etc. Right, and look at grown biofilms on the media. Okay, so at the influent end, because you have high concentration of substrate, you could obtain rich biofilm, thicker, right, more active. At the effluent end, okay, it's less intensive. And what happens? Mass transfer. Right, mass transfer. We're not trying to model the process. I just simply explain this to you because it's very complicated here, and we cannot solve the equation or process modeling mathematically, like analytically. Okay, you have to use certain programs to solve this equation. Not as easy as we did for the active sludge process. And here you have a biofilm, and this is the media surface, and this is bulk liquid. That's our wastewater, right? And the organics need to diffuse first to the surface of the biofilm, and then transport inside. Okay, and the organics will be consumed within the biofilm. Okay, within the biofilm. So you see decrease of organic concentration. Okay, of course we could write all these mass transfer equations, and we have certain boundary conditions, and based on these boundary conditions, you can solve these equations. Okay, and here we do have calculus. This is very complicated. Boundary conditions. I'm not going to go into details. And then what do we do in terms of design? Empirical, right? So empirical is much more convenient in designing of trickling filter. For example, plastic media, we have the German's equation: SE effluent concentration S naught influent equals E to the minus KT divided by Q to N times D. KT is trickling filter reaction coefficient. It's a measured parameter. Okay. D is packing depth. Right. Q is hydraulic application rate. What is hydraulic application rate? Q divided by A. Q divided by A. Kind of, but it's a little bit different here, considering the flow rate. The flow direction, right? The flow direction. So here it's not the superficial velocity. So previously, what's the direction of flow? And here, what's the direction? Here, the flow direction is from the top to the bottom. Okay, so it's vertical. It's vertical. Right? How can we determine KT? Right? We determine KT from a benchmarking experiment. And we have K1. K1 is determined from some plant studies. You have different wastewater, you have different K1 value, right? And the value is measured at certain condition. Like the depth is 6.1 meter, influent BOD 150 milligram per liter, right? And you have your design system, and we are benchmarking your system with this one, right? To get your K. And also we need to consider temperature effect. The value is measured at 20 degrees Celsius, so we need to correct the value based on temperature. Okay, based on temperature. The second empirical equation is called the modified Wells equation. S in divided by S out. S in influent substrate concentration. S out effluent. Right. R is recycle ratio. Recycle flow rate divided by influent flow rate. It's the same as R. Okay, little r we used earlier. Right. K20 is the same value. Right. Rate constant. AS specific surface area of the media. H height. Theta. This is a accounting factor for temperature change. QI influent flow rate divided by surface area. Okay, surface area. When you use the modified Wells equation, pay attention to the units. Here we have two sets of units, international and US. Okay, for different unit system, you have different values. For K. Okay, different values for K. There will be one homework problem on this. So pay attention to the unit. Okay, then you pick a value, and also be very careful when you plug in all these numbers and do the calculation. It's all about calculation because the equation is already there, right? You plug in the numbers, and sometimes you have to convert the unit, and be very, very careful. Okay, and you do not have to memorize the equation. Okay, if it is needed in the exam, it will be provided in appendix. Okay, makes sense, right? And the third type is for rock media. So previously we were talking about plastic media. For rock media, we use NRC equation, okay, based on statistical study on miniature basis. For single stage, this is removal efficiency equals 100 divided by 1 plus 0.4432 square root BOD loading divided by volume divided by recirculation factor. What is recirculation factor? Recirculation factor is a function of recycle ratio. Okay. So we do not have a lot of things to explain here because they are empirical. So this is obtained by feeding the experimental data. Okay. If it's two-stage, you just plug in the first stage data. Okay, like removal efficiency from the first stage, etc. Okay. We don't have to spend a lot of time because all these equations are empirical. Okay, empirical. That is trickling filter. I want to emphasize again, trickling filter is not a filter. This has been tested multiple times. Ask students, trickling filter a filter? Okay, so it's not a filter. It's not like standard filtration, like membrane filtration. It's a biological reactor. Another attached growth treatment scheme is rotating biological contactor. Okay, so it's rotating. Okay, it's rotating. So here we have many discs. It provides a surface for the microorganism to grow, and there they develop biofilms, right? And the submerged portion could be around 40% into 80%. Okay, to 80%. And what happens? It is rotating, right? So when wet, organisms get organics, because that's when the microorganisms get in contact with wastewater organics in the water, right? When in the air, organisms get oxygen from atmosphere. So far for our biological wastewater treatment, we have been focusing on aerobic treatment, right? So aerobic treatment means oxygen serving as electron what? Electron acceptors. Okay, oxygen serve as electron acceptors. So you see, every step we need oxygen, right? We need oxygen. For trickling filter, you see there's spray, right? Spray of wastewater. So during the spray, the water droplets get in contact with air. So there, the droplets pick up certain oxygen. Okay, pick up certain oxygen. It's covered so sunlight does not degrade the plastics, right? And these discs are large, 3.6 meter in diameter. Right? Look at some pictures. These are the discs. On the surface, we have growing biofilms. We do have some in Hong Kong, like maple pin, Hen Chow, etc. Right? RBCs. Right? Small scale. So how we design RBC? Again, empirical. Okay, empirical. Depending on which stage you calculate, right? And stage, right? For attached growth treatment scheme, we should always consider soluble BOD. So S is soluble, right? Soluble. Because earlier we talked about the biofilm. The organics need to get into the biofilm. Only soluble organics can get into the biofilm. Okay? So it needs to be soluble BOD concentration. Soluble. AS is disk surface area on stage N. Q is the flow rate. So this is continuous flow. Soluble BOD is about half of total BOD. Okay? It's about half of total BOD. Any questions so far? Suspended, attached, right? So attached we have trickling filter and we have rotating biological contactor, RBC. So lastly, let's compare attached and suspended. Right, so we do not have trickling filter in Hong Kong, as far as I know. Okay, we have some RBC, small scale, but we do not have trickling filter. So typically trickling filter occupy a large area of land, right? You see, for our biological wastewater, like shot in, it's PFR, active sludge, okay? Plug flow reactor. Advantages of attached growth process, less energy required. That's really, right? We do not see aeration, right? Aeration. Sample operation with no issues of mixed liquor inventory control and sludge wasting. Right? And no sludge bulking in secondary covers. We did not talk about this because of time. That was one problem that could happen in active sludge process, sludge bulking. Less equipment maintenance needed. Better recovery from shock toxic loads. But you can imagine poor effluent quality in terms of BOD and TSS. But that's relative sense compared to active sludge, right? Greater sensitivity to lower temperature, and also odor production. Because that happens in absence of oxygen, anaerobic condition. In a trickling filter, for example, it could have certain location which is lack of oxygen, right? It's deep. But in active sludge, we have aeration. So you have a lot of oxygen. And here, we could have hydrogen sulfide produced. Right? Uncontrolled slot sloughing event. Some biofilm could come off from the surface, and that could be a problem. Difficult to perform nutrient removal. Next lecture, we talk about nutrient removal. Higher turbidity. So not as good effluent quality as that from active sludge process. Okay, so that's still attached gross treatment scheme is mainstream. You can find treatment filter in some other places, right? Active sludge is probably the most popular type, so we spend a lot of time. And we have some we call low-tech technologies, like ponds, lagoons, right? A lot of land is needed. Okay, passive treatment usually a series of ponds, lagoons, aerated ponds, right? Yeah, variable detention time designed to be aerobic. If you want the pond to be aerobic, it needs to be shallow, right? So the oxygen could transfer inside. If it's deep, there could be anaerobic portion. So it's typically shallow, maybe mixed or stratified, have a long HRT to allow algae to produce oxygen. So we could grow algae to produce oxygen that's beneficial for wastewater treatment. Right, some comparison, oxidation pond, anaerobic pond, aerated pond. Right. Right. So it's not very relevant to our case. I'll skip this part. Any question before I let you go? No? So for the two lectures, a lot of content, right? Very condensed. Spend more time. Please spend more time. Okay. The next lecture will be on nutrient removal. It will be a guest lecture. All right. Okay. See you.